let's continue with our series in linear algebra, specifically where we use matrices to help us solve systems of linear equations. So in our first little video, we really set up the idea of representing a system of linear equations, which is just, in this case we have two equations with two variables, x and y, and we take just the coefficients to set up a matrix. Remember, we have to line everything up, so we have x and y, and then the first row represents our first equation, and our second row represents our second equation. So we have 1, it's a secret 1 there, 1, 4y, and then we augment this 2 by 2 by adding this line, and then putting the negative 2 here, and then 2, 3, 1. So basically we are just reading across, right? We're just reading across and just getting rid of these variables so that it saves us some time. So we can do this for more variables. If you can imagine having like 10 by 10, you could let a computer do that for you in reducing and, working with the matrix, but we're going to just follow through with our 2 by 2 case for now. Just remember that we always need to line everything up. So in the case of this example that we already worked through, if we're missing a variable, like if we line up A, B, C, and we don't have a B term, you just put in a 0. So last time we kind of set that up, and then we also started developing the idea that our goal is now then to take our matrix and get it into something that looks like this. Because if I have this matrix 1, 0, some number, 0, 1, and then some other number, and then if I expand this back out, like if I write this matrix in terms of a system of linear equations, I get 1x plus 0y equals this number 1, and then 0x plus 1y equals number 2. And if we simplify that, we know 1x is x and 0y is 0, so that goes away. So this first row is actually x equals number 1, right? And then the second row is y equals number 2. So, and that's our goal, that's our answer, right? We want to solve, when we solve a system of linear equations, we want to know the exact value or values, if any, of each of the variables, so that if we plug each of the corresponding values back into each of the equations, all of the equations should be satisfied. They should be true, right? So that's what it means to have a system of linear equations. We want to solve them simultaneously. So if we have x equals some number and y equals some number, we've essentially solved this equation. We just want to know what those numbers are. So we now know that we're trying to go from here to here. Now the question is, how? How do we take this matrix to this matrix? Now essentially, we're going to build more intuition today, and we'll kind of put it all together, all these steps together into some practice problems. But right now we're still developing step by step. So the key thing for today is to remember that everything that we do to this matrix, we are still just using it as shorthand to represent an actual system of linear equations. So we can't just like arbitrarily do things to this, because in our minds we can remember this is a representation of this. So essentially, you just need to keep in mind what you already know from algebra. Okay, and we will go back and review more algebra moving forward, of course, but I'm assuming that when we're working with this linear algebra, we already are pretty comfortable with this, even though we might need a little bit of review. But whatever you do here, there's like an equivalent, what we call row operation with just the matrix, okay? And as long as we keep in mind, like, you can't just break math, you can't just randomly add things where it doesn't work. You can't do that here. So usually when we talk about row operations, there's really only a handful of them. And since I've been tutoring students in this, it seems like different professors and, textbooks and stuff will write these row operations slightly differently, but they're all like just subtle variations of each other. And so, if this looks slightly different from something that you've learned or are learning, maybe you can adapt it. But that's also why I want to take the time here to build the intuition about what's really going on, so that you can adjust to like what it is and how you're learning it, right? And even just notation varies. So the key thing is that row operations are equivalent to working with our normal algebra steps. So let's just continue with this example. So let's say I have 1, 4, -2, 2, 3, 1. So if I were to try to solve this, okay, so apart from, you learn different methods to solving this. You can do, substitution and whatnot, right? But we're really going to be focusing on the elimination method with matrices, because it's not convenient to substitute one variable. It doesn't really make sense with matrices. You kind of want to work with the entire row, like row operations, okay? So what that means is, if I were to solve for this using elimination, you might remember this, but you kind of want to be clever in what, like, I might notice, okay, this, and I have an x and a 2x, and I want to eliminate one of my variables. So if I were to multiply this equation, this top equation, by, depends on what you want to do, 2, and then you subtract the two equations, you get, for this part, you would get 2x minus 2x. So the x's go away, and then, of course, you have to do the rest. Or you can just multiply by -2 and add, which ends up being the same thing. But the key thing is you're essentially multiplying an entire equation, right? So that's an example of a step that you would be doing and a row operation. So let's just start with something that doesn't work, for instance, okay? Because this might just emphasize what a row operation, like what a valid row operation is in this context, okay? So we're only talking about in this context of solving linear equations. So let's say I do row 1 plus 3, okay? So this is row 1 and this is row 2. So when we write like row 1 plus 3, we're talking about every element of the row, okay? We're not just doing one term, we have to do the whole row. That's why they're called row operations. So I would basically do 1, and I guess since this is the first time that we are doing this kind of stuff, I'll just write out 1 plus 3. Then we have 4 plus 3. And then line -2 plus 3. Okay, so again, every element of the row. And then we can just keep the second row as it is. So again, one row at a time. Or you can do them simultaneously if you can keep track of that. But essentially you would be, if you really want to write one row at a time, you would change one and then you would change the next. Okay. So then this would give us 4. 4 plus 3 is 7. -2 plus 3 is 1. And then we keep the second row as it is. So the question is now, okay, so we've gone from here to here. Now the question is, does this matrix represent an equivalent system as this one? And so let's try and write this back out. Let's say we still have our x and y. Everything still needs to be lined up. The line still equals. So now we would have 4x plus 7y equals 1. And then the second row is the same still, so 2x plus 3y equals 1. Is this system the same as this? Are these two the same? And the answer is, well, we have some kind of issues here, because 2x plus 3y equals 1 is the same. That's fine, but it kind of just breaks math. This equation and this equation are not the same, nor are they equivalent, because there's no rule in algebra that says you can just randomly add 3 to each coefficient, right? So this is actually adding a constant is not a row operation. Not row operation. Okay? So for row operations, we're talking about them in the context of algebra, steps from algebra. Okay? Now, of course, if you add matrices and stuff like that, you can work with matrices, and you study a bit of that in linear algebra as well, or when you're taking inverses and stuff like that. That's fine, and that's a different thing. Like, that's a completely different concept and different idea. When we talk about row operations, we're talking about trying to take one matrix and getting it into a different form, while keeping in mind that it's used to solve linear equations. Okay, so then what are the row operations? Well, starting with what not to do, we can, like we kind of mentioned, if we were to try and solve this, we can multiply, right? Because remember, in algebra and also in like pre-algebra, right, if I have let's say we have 2 equals 2. If I multiply by 3 on this side, I multiply by 3 on this side, it stays balanced, right? So whatever I do, that's the awesome equal sign here. If I multiply by 3, then I multiply by 3, I still get 6 equals 6, right? And it's the same when we have a whole bunch of other stuff like x and 4y, right? It just looks a little bit messier, but we still have our equal sign. So I can, if I were to multiply, in just using our normal algebra here, if I were to multiply this equation, x plus 4y equals -2, by 2 on both sides, because I'm looking ahead at my elimination, right? It makes more sense to multiply by 2. an alternative would be to multiply this equation by 3 and this equation by 4 so that I can eliminate y. But that's just more work. And if this part is all getting confusing and you need to review some algebra, just let me know and we'll eventually get there here on this channel, but let me know. But here we can, for instance, multiply both sides by 2. So I'm going to just write that in. 2 and then parentheses 2, right? So we would have this, but if I were to do 2 times x plus 4y, remember we need to do the distributive property. So I get 2x plus 8y equals negative 4. And that would be an equivalent equation to my first one. And so if you notice, I basically multiplied by 2 times 1 is 2, 2 times 4 is 8, and 2 times negative 2 is negative 4. So when we write that back out as a matrix, I've multiplied the entire row by a constant, in this case 2. So a row operation is to multiply, whoops, stuff there. Okay, old math stuff. Okay, so we would multiply by a constant, and what that is a valid row operation. So row operations, we can multiply any row by a constant. So I'm going to call that constant C, and I'm going to multiply by row whatever, like row, let's just call it row I, okay, where I is like the number, like row 1, row 2, row 3, so 1, 2, 3, etc. So remember, when we have like a huge case, a 10 by 10 case, we can have 10 rows, right? So we multiply every term by this constant. That's what this means, okay? So, whoops. Let's see here. Okay. So, sorry about that. I didn't realize I had some notes in between, but basically I can multiply an entire row by a constant. So that's kind of what we're doing here. Like when you solve normally, we're multiplying an equation by, let's say, 2 on both sides, or multiplying by 4 on both sides. When we distribute that out, it means that we're multiplying every coefficient by that constant, which is the equivalent in our matrix. Since our matrix only represents the coefficients in the first place, we're just multiplying the row by a constant. And then another operation is to be able to add the two rows together, right? So once we do 2x plus 8y, in this case we would be subtracting, but we know adding and subtracting are essentially the same. You're just adding a negative to get minus, subtracting, right? So we can basically add these two together or subtract these two together. So if I were to subtract or add, right, we're adding every coefficient. So I guess I should have started by multiplying by negative 2 to really show the addition, but in this case we're going to subtract. So we do 2x, okay, let's write this again. We have 2x plus 8y equals negative 4, and then we have 2x plus 3y equals 1, right? So once we multiplied by 2, we have an equivalent equation, but this one's easier to work with because if we subtract, we're subtracting every term, right? Can we distribute the minus? So we'd have, this part goes away, and we'd have 8 minus 3y equals negative 4 minus 1. So 5y equals negative 5. And since we're not doing algebra right now, we can review that another time. But the point here is that when we add or when we subtract, we're subtracting or adding each element of each row. Like we are lining them up and we are adding or subtracting as needed, right? I wrote a minus here, but essentially you can think of it, the minus, as a plus, but distributing this -1 first and then adding, right? So I would be really doing 2x plus 8y equals -4, and then -2x minus 3y equals -1, and then adding each term, this, and this, right? So I know the -1 stuff was a little bit roundabout. I could have just multiplied by -2 in the first place, but whoops. But either way, just to give you an idea that plus and minus are basically the same anyway, you can take your c constant as a negative number. So c can be anything, any constant, as long as you're multiplying it to every term, right? And so then we can add or subtract. So we can do row I, whatever, row 1 or row 2, plus row j, right? Where I and j are just our normal like rows, right? Indices. I'm indexing the rows. I'm just trying to generalize. So you could do like constant times row 10 all the way across, and then row 3 plus row 7. You know, like as long as you're doing it to every single term and lining it up. So then the last one is we are allowed to just switch the rows as we want. So row I being swapped with row j, because I mean, you can see since it's a system of linear equations, it needs to satisfy this equation and this equation. And so if we switch the two, it's this equation and this equation. So 2, 3, 1, like this. 1, 4, -2, and 2, 3, 1. If we were to switch these rows, 2, 3, 1, 1, 4, -2, it's an equivalent matrix. And you might have reasons to do that just as we eliminate or as we work on this elimination process. It might make it easier to help us get to 1, 0, 0, 1, right? Because you might end up, as you work through these kind of operations, you might end up with like 0, 1, 1, 0. And in that case, you would definitely want to just switch the two rows without it being super complicated, have to go back and redo everything, right? So switching out the rows would be convenient. So I just wanted to build the intuition. It's a little bit like just like leaning into it slowly, without just, suddenly doing all these operations. So when I write it like this, I basically just mean adding row 1 and row 2, for instance. So people write this out slightly differently. Like, what I mean by adding it, you're gonna replace a row with all of the sums, and you label which row you're going to do that to. So if I started with this, for instance, I would keep, and I can decide which row to do that for, but I can do 1, 4, -2, and keep that. And then I can, if I wanted to. In this case, it's not going to be helpful, but I can just do 2, like everything in this row added to that row. So 2 plus 1 is 3, 3 plus 4 is 7, 1 plus -2 is -1. And so this would basically be row 2 plus row 1. Does that make sense? Like, you're basically replacing a row with whatever it is that you just did. And some people even write like row 2 becomes row 2 plus row 1. You see what I mean? Like, you're replacing the row with it. So whatever notation you're comfortable with or learning in school, that's totally fine. It's really, the important thing is to keep track of what you're doing. And so while we're at it, these are the 3 main things, the 3 main row operations. But while we are at it, you can kind of see here that we can combine these first two, as adding what's it called, a constant times 1 plus another constant times the other, and doing that all in one step. So like C1 Ri plus C2 Rj, and replacing one of the rows. So this is more like the shortcut. This is a shortcut, but you can kind of see how 1 and 2 combine to be something like this, because I can multiply any row by a constant C. So I could multiply even row J by constant C by a different constant and add those together. And so the equivalent of this is essentially doing this entire thing in my head to think this minus 2 times that, this minus 2 times that, this minus 2 times that. Because when I say this, I'm multiplying this row by 1, just keeping it the same, and then minus 2 times this one. So I've multiplied one row by one constant, 1, and the other row by another constant, -2, and then added. So it's just like doing it all in one step. Okay. So really, you only need to, you could almost argue that these two are the same if you considered, or like this one encapsulates 1 and 2, if you considered 0 as being a valid constant. Okay? And that's really all you're doing. You're switching, you're multiplying, and you're adding. And those are our main row operations. But when we say we're adding corresponding terms, okay, that line up. So from here, I think we're just kind of la-di-daing a little bit, but I hope that it's interesting. Like, I'm just kind of walking you through ideas, and if you have any questions or you want to kind of experiment, if there are any other row operations to do that work for linear equations, you can do that. And I think it's really interesting to learn this way rather than just like straight up telling you, okay, these are the row operations. But we will get there. The next video will be actually solving this. And then we will work through more complicated situations too with more variables. But we're working our way there. Wanted to just take some time to build this intuition. I know it's kind of messy right now. We will go back as usual to do practice problems, like specific practice problems, but before just jumping into the, A, B, C, do this, do this, do this, I wanted to just hang out and explore and encourage just trying, even without a specific direction, because I think there's a lot of learning that happens when you figure out like why something doesn't work. So, I hope that this was fun to just kind of play around with the ideas. It gets you thinking. And if you are, maybe it's a nice little like distraction, but if you're like, whoa, I'm not gonna think anymore, I'm gonna go to sleep, then I hope that you have some sweet, sweet dreams. Maybe you tuned me out already, which is more than welcome. If you are here just to fall asleep, I hope you have very sweet dreams. And if you are interested in this, I hope that this is relaxing. And I will see you soon.